Okay, anyways. Geez. What were we talking about last time? What was like the main overarching topic that we were trying to get at? Yes, we're finally out working on something real. We're working on the H atom. We talked a little about Coulombic potentials. Why do we care about Coulombic potentials? Like, what was that related to? Yep. So we were trying to come up with the Schrodinger equation to describe an H atom. Give me the generic Schrodinger equation again. Yeah. Yeah. And that looks so simple and nice. It's never that way. We started talking about Coulombic potentials because we had to consider what the Hamiltonian was comprised of. And we were thinking about the attractive and the repulsive forces in an H atom, right? We also were thinking about the kinetic energy portion of things and the potential energy portion, contributions to this. So in terms of how many terms did we have for this Hamiltonian, and what were they related to? Yes, and we have to have 3. Why do we have to have 3? Yep, and what were the kinetic energies for? Yep, did I write it that way? So this was kinetic energy of the electron. What else do we have? Yep, I'm going to shorten it just to nuke. And then what was the last thing? Yep, and that's where that Coulombic potential came into play to describe the nucleus-electron interaction. And we described the things that this potential would depend on, and we arrived at the following expression, R, where the potential only depends on R, because are we really changing the value of the charge of an electron ever? No, it just always is. We say -1 or at least some amount of coulombs. And then will the nucleus in this case change? No. It will change depending on whatever atom we're looking at, but we're just considering a hydrogen atom. That won't change. And we ended up with as our expression. Okay, we're going to delve into these other ones a little bit today. Those are pretty easy because, like we talked about last time, what are they going to look like? What has it always been for the kinetic energy? Yeah, -h bar squared over 2m second derivatives, right? That's not going to change. That's nice. Okay, but I want to look at this term, and I want to talk about it a little bit more. So the first question I'm going to ask associated with it is, why is there a negative sign? So why is there a negative sign? Well, even though I did tell you. Yeah, it's an attractive force. Okay. Why would an attractive force... Sorry, I'm trying to tuck my shirt in so I'm not like flashing people. All right, I don't want to say that on camera. I'll talk to you guys about that afterwards. That's a fun one. So that's, yeah, it's an attractive force. Why would an attractive force be negative? Yeah. It lowers the energy. Okay. Something to keep in mind when we start looking at more complex multi-electron systems, if it's energy lowering, it's an attractive force, right? It seems really weird in some cases that an atom will even form because we're packing in a bunch of negatively charged particles near one another, and really they don't want to be near one another. Like even when we talk about electrons occupying an orbital, they really don't want to do that, but they do that. So it's a combination of these attractive and repulsive forces that can make molecules and atoms form. It's just by happenstance. Because otherwise, they wouldn't form, we wouldn't be around to talk about it. Okay, let's talk about the kinetic energy portions. So let's return to K. K hat. Nothing super special there. Let's talk about the kinetic energy portion of the electron. What's that going to look like? Yep. We're going to express that second derivative with the upside down delta, the gradient sign. And what we want to do is we want to indicate it has to deal with the position of the electron. What do I have to do to that mass value? What's it the mass of? Yeah, the mass of the electron. So that's what we have here. If you notice, negative sign. So what does that mean? What's it going to do to the total energy of the system? Yep, it's going to decrease it. Ends up being a favorable interaction. Now, what about the nucleus's motion? What's that going to be? Yep. Well, this case, it's the mass. We're going to be generic to say mass of the nucleus, but it would just be the mass of a singular proton. And then what about our gradient? Yeah. Of course, again, this is a one electron system, or well, we're talking about just H1, no neutrons in there, but that could change with the neutrons. And it does impact the wave function that way a little bit. Okay, so now what does our total Hamiltonian look like if I can find an eraser? Damn it. And my fancy little chalk. Did Dr. Ruprecht have you walk over and do stuff on that side? Or? Yeah. When I teach inorganic, I usually use like everything. So that way people have to go over there and draw stuff. Your guys' class, you'd only have this board though. Does Dr. Ogawa make it go up or no?
No, but he makes us like, he goes in order and makes us ask questions.
I get that. That's when she got out of the exam super fast. I was like, whoa, that was quick. She's like, I'm here for funsies. So now what does our Hamiltonian look like in like complete mathematical jargon? Yep. What else? Yeah. Yep. And then finally, yeah. Okay. So we're at this point. This is kind of tough to deal with because how many moving things do we have to worry about? 2. We got to worry about the motion of what? Yep. The electron and the nucleus. Those are the only 2 things we have to worry about, though, right? We've seen other quantum systems where we have 2 particles that we have to worry about, and we simplified it so we could make the mathematics way easier, not have to worry about 2 things in motion. What are we going to do to make this easier? We could show that they're separable. I want to do something even before that. It's related to a constant.
Make stuff 0.
Make stuff 0. We always are trying to attempt to do that. We're not going to do that in this case. All these things you are suggesting we're going to do after the fact, which is good. Maybe not the set stuff to 0, because we can't do that one here. In the harmonic oscillator, when we had a 2-bodied system, this is Navy SEAL hand signals for harmonic oscillator. What did we do there to get away from having to worry about those 2 particles? Let's check back in your notes, look back. What's a simple way to go from having to worry about the motion of 2 things to the motion of 1 other parameter? So we talked about it for a diatomic molecule. Yeah, it's reduced mass. We can use a reduced mass, and then we can collapse these 2 terms kind of down into 1. So we use reduced mass. And what symbol did we get for reduced mass? U. Yep. And how is it going to change that Hamiltonian then? Yeah, we'll have 2 terms, and what's the first term, the kinetic energy term, going to look like? Yep. We're going to leave the gradient like that, and then what about for that other bit? Yeah. That bird is so loud. Sorry. Yeah, exactly. We're getting more nature. I say that and then I get grumpy at animals making noise. Okay. So now we have our Hamiltonian. What are we going to do next? Yeah. We got to find a wave function that will satisfy this Hamiltonian and will spit out an energy. We got to go back to the generic. Schrodinger equation. Okay. This gradient, if we look at the different parameters we're going to have to differentiate with respect to, what are we going to have to differentiate with respect to? Yeah. So what would our parameters be that the wave function would depend on? Yep. R, what else? It's the stuff that we're going to differentiate with respect to in the gradient. It could be X, Y, and Z. We get to a point where we can't separate things out that way. Yeah. Okay. So that's how we're going to define our wave function is it depends on all of these things, right? Okay. This term, what does it only depend on? It only depends on R. So what we're hoping we can do is, what would be the best case scenario, or what did we do with particle in a 3D box? Oh yeah, we could say R is constant. Can't do that for our atom this time. What would we do with our wave function? We would separate it, right? We would have a function for X, Y, and Z. We can't do that completely. What we can do is we can separate this into two different functions. We have one just for R. This guy is known as the radial function. Portion. What about the other one? Yeah. What symbol did we give for any functions we had in the past that depended on theta and phi? No, oh, well, we did do that. But then we showed they're not really separable from each other. They're not really independent of each other. We had another function. We gave the symbol y. What were... And what quantum numbers did we need down here? Yep. And what did this function depend on? Yep. And do you remember what the name of this thing was called? Spherical. Yep. I haven't indicated it yet, but what we are going to see is this depends on the principal quantum number, n. Okay, so why can we do this? Thanks to the potential only depending on R. And it being what's termed as centriosymmetric. The wave function can be separated into an angular part and a radial part. What's the radial part? Yeah. Big R of R. What's the angular part? Yeah. Okay. The benefit of this is we've covered the spherical harmonics. We've beaten that portion to death, which is nice. We got to worry about the R part in a little bit. But before we even do that, what do we need to consider, or what should we try to consider? Well, we actually haven't proved this. We haven't proved that it benefits us. And we want to see if we plug this into the Schrodinger equation, is it actually separable? Like, can we get an energy term that's responsible for that versus that? Can we show that including this benefits us? So the next question we're going to ask is can the Schrodinger equation be separated? You probably know the answer to that one. What do you think the answer is? Yeah. The answer is going to be yes. But we want to go through and show how to do that. Because I don't want to write what depends on what a million times and save us some time writing, what we're going to do is just say the wave function is equal to Ry, like that. Of course, when we say that, we really mean this bit right here, right? It's just a shorthand. Okay. So now what we want to do is we want to start with our Schrodinger equation, and we want to utilize that Hamiltonian and see can we separate everything out. Am I okay to erase this side? Okay. So we got H psi E psi. Let's plug stuff in for H. Negative H bar squared over 2m partial psi. Then we got B psi is equal to E psi. We said that psi is equal to R. What we're going to do next is plug that in. See what happens. Shit, we should have used reduced mass, my bad. There we go. That looks better. Okay. So let's plug in what else did I forget? Yeah, I forgot a squared here. Okay. So now let's plug that in. What color do you want R? What color do you want the angular one? Okay. And then what about Y? Blue? Yellow? Oh, conflicted. Will tiebreaker. What do you want? Yellow. All right. Yeah, outvoted. Sorry. And remember that that V is still an operator, which we'll talk about in a minute on how to deal with that. E. Okay. This gradient, what's in that gradient again? Yep. Right. It's not like as simple as like that for X, Y, and Z, where that would be the case for X, Y, and Z. There's other things that have to get tacked in because we have spherical polar coordinates. We came up with a way to express the stuff just for the angular momentum part of things. We had that symbol capital lambda squared, right? In spherical polar coordinates, we could break this apart into some portions that depend on r and the others that depend on theta and phi. So what we are going to do is break that apart into those terms. We get partial with respect to r squared plus 2 over r partial with respect to r, 1 over r squared lambda squared r y potential r y. Okay. This is a little bit different than we've had to deal with in the past because this r is changing, right? Or it has the potential to change. Let's apply these derivatives to the parts of the function that we would need to apply the derivative to and leave the other portion a constant. So what I mean by that is if we take the second derivative with respect to r of both of these guys, which one do we really only have to worry about? Yeah, capital R. Why don't we have to worry about this y? Yeah, it depends on theta and phi, so it really is just counted as a constant. So if we do that, oops, forgot. And what happens to the y? Or the angular momentum function? Or the angular function, excuse me. Yeah, we just tack it on there like that. Okay. How would you express, oops, sorry, that was meant to be yellow. How would you express the second term then if we were to apply it? Mm-hmm. Yeah. We'll go. Yep. And we could just conglomerate that times y right up there, right? Okay. The last term. So which 1 over r squared? Yeah. Because remember, what does that lambda depend on? Yeah, theta and phi. So we got y in there. And then the potential r, y, and what's that all equal to? Yeah. Okay, what would you suggest to do next? Yep, we want to divide by ry. The reason for that is we'd be able to get rid of the y here and the y there and the r here, right? What else would we want to do besides dividing by ERY? Yeah, we're gonna do that part too. Okay, so let's say we divide by ry, capital RY. This function, what's it only going to depend on? R. What about this function? What about this portion? Depends on y, but what else is still stuck in there? Little r. So it still kind of depends on the radial part. What could we do to get rid of that? Yeah, so we're going to multiply by r squared divided by what? Yeah. And now what we're going to get is we'll have a handful of terms. We'll get rid of some stuff, but we're going to introduce some new things. So let's rewrite everything. Negative h bar squared over 2m. Oops. R squared. Second derivative with respect to r. Capital R. What else do I need here? Yep. Whoa. Over R. The second term, what's that going to look like? To R over what? Yep. R. Times what? Yep. Last term. Mm-hmm. Okay. What happens with the potential? Yep. R squared times V. And then it's equal to what? Yep. Okay. We're going to rearrange this a little bit, but let's go through what does this depend on? R. This term. R. These guys. Yep. Y, which means theta and V. This thing. Keeping in mind that the potential only had what parameter in it? Had R. Yep. So what we have shown is yeah, you can separate it. So would you rather we rewrite it and say all of this stuff is R, or do you just want to go underneath and point out which things are R? That's fine? Okay. So this stuff depends on R. Oops, little r. This term here, what's it depend on? Theta phi. This term. Yep. Okay. The cool thing is we've already done this with our last model system, particle on a sphere. We've already solved the Schrodinger equation for that. So we can utilize that to our advantage. So we have a solution. For the theta and phi part. What was the solution to that one? Negative L times what? Yep, L plus 1. And then that is if we look at the energy, right? Yeah, it's just Y back out. So put that in yellow. So therefore, if we apply, shoot, these shouldn't be M's, they should be reduced masses. I got lazy. If we apply that to this portion here, all we need to do is just tack in this little bit, and we get what will, after I reduce everything down, what will my answer be? Yep, the Y's are going to cancel, which is great. What else do I get? Yep, negatives cancel. So we get L plus 1 times what? Yep, h bar squared all over. Yeah. Okay. What we're going to do next time is we're going to plug this in to here. And then we're going to explore how do we handle the rest of this, the radial parts, to make it work out to what we need.